Swayam Prabha. Digital India. Educated India.
Welcome back to a new lecture on control systems. In the previous lecture we have kind of completed our excursion into these Bode plot blocks, different constituent blocks to an extent, with a look at what a typical second order factors Bode plot looks like. By a second order factor I just mean that it is a pair of complex poles and zeros, and in the figure before you now you can see that, well, we saw that the lesser the damping, we saw that with a lesser damping you have a higher resonant peak, just like with a lesser damping in the time domain you had a higher percentage overshoot. And we also saw that this peak had a tendency to shift more to the right, closer and closer to omega n, which was the break frequency, as zeta diminished. In the phase plot we saw that the role that this zeta played was in determining the steepness of rise. So to quickly recapitulate once again, we saw that if you have a phase function that looks like this, as we have derived already, the phase function looks like this for a second order factor, then you see that as omega tends to omega n, the imaginary part of this complex number, which is sitting in the numerator here in the tan inverse argument, right, depends on zeta. So if zeta is very small, then both the numerator and the denominator are small values as omega tends to omega n. So therefore you might think of something like this, right, and as omega switches from being smaller than omega n to being larger than omega n, the sign flips in the numerator, in the denominator, and if the sign of the denominator flips, it means that there is a transition of the complex number from one side to the other, such a transition like this, right. Now you see that of course if zeta is very small, then the numerator is also very small, so you basically have a greater phase shift as omega transitions from, let's say, omega n minus epsilon to omega n plus epsilon. On the other hand, if zeta is also very small, if zeta is also very large, rather almost close to unity or maybe 0.8 or thereabouts, then this is not so small after all, so then the imaginary part is larger. You can immediately say that the imaginary part is comparatively much larger than the real part. So then also there is a transition from one side to the other in the real part, but the net angle, so the entire argument hinges on this, that if you look at the net phase change here, and if you look at the net phase change here, obviously this phase change is less than this phase change. So this is phi 1, this is phi 2, so this is obviously less. So as you increased zeta, you got phi 1, and as you decrease zeta you got phi 2. So that means as omega transitions from one side of omega n to the other side of omega n, that is from being less than omega n to being greater than omega n, you see that for a higher value of zeta the phase change is lesser. So for small changes in omega, the change of phase is smaller for higher values of zeta, but for smaller values of zeta, as omega n flips from one side of omega, as omega flips from one side of omega n to the other side, there is a greater phase change. So that means there is a steeper rise in the phase plot for smaller values of zeta, right. So that gave rise to this particular observation, that as zeta decreases the steepness of phi omega increases. Okay. So, having seen all of these constituent blocks, we are now in this lecture in a position to consider a typical transfer function, say for instance something like this, yeah, s plus 0.2 divided by s into s plus 10 into s plus 50. Now, we know what individually these constituent blocks, what their Bode plots will look like, but of course the first thing we have to remember is, before getting any further, we have to pose it or cast it in the form, in a standard form. So, this is a standard form for the root locus, we have seen that, yeah, in the product of the poles and the product of the 0 factors, yeah, in that form. So, this is ideal for root locus application, but for Bode we need to change this a bit. So, what are we going to do? We are going to just write it in this fashion, where we are going to pull out this j omega upon 0.2 plus 1 times 0.2. Yeah, of course we have the 5000 sitting over here. Of course we have this j omega as it is, because it is an integrator, and then we have this 10 pulled out, and we have 1 plus j omega upon 10, yeah, and then we have the 50 pulled out, and we have 1 plus j omega upon 50. Now, having done that, we are now in a position, you see this 10 into 50, that is 500, which cancels out with this 5000 and gives us 10, yeah, and then this 10 multiplied with 0.2 gives us 2. So, this therefore equals 2 upon 1 plus j omega by 0.2 divided by j omega into 1 plus j omega by 10 into 1 plus j omega by 50. So, let me color code that. So, this is my constant block, this is a first order 0, this is a first order pole, this is yet another first order pole, and okay, let me use some other color, maybe let us leave it black, yeah, this is the integrator, right. So, now I am trying to draw the individual constituents and their Bode magnitude plots, okay, and then I am finally going to add it up. So, let me just make enough room here. So, first I am going to draw this magnitude, and then I am going to try and draw the phase plot in the same graph if I can. Let us see, this is 20 log m omega, and this is phi omega, this is of course the omega axis, this is also the omega axis, right. Okay. So, let us see what is a reasonable range of omega to choose from. What are the corner frequencies or the break frequencies? We have 0.2, we have 10, we have 50. So, it seems like if we can choose a range of frequencies starting from 0.1, it should be good, but let us go one decade below, right. So, let us start from 0.01. So, let this be say 0.01, then let this be 0.1, then let this be 1.0, then let this be 10, and let this be 100, and let this be 1000, yeah, all right, and we are good, okay. This does not look very nice, so let me try and draw this line a little better, yeah, okay. So, now we are supposed to be able to construct this entire Bode plot by just looking at each individual block. So, what is this red block going to give me? So, this red block is going to give me a constant line 20 log 2, which is log 2 is 0.3. So, this is 0.3 into 2 is a 0.6 into 10 is 6 dB. So, it is a flat line at 6 dB, okay. So, let me have this 0 dB line here, this is 10, this is 20, or rather I can actually make it in scales of 20, because these are, after all, minimum is 20 dB per decade. So let me just make it 20, let me just make it 40 here, let me make it minus 20 here, and make this minus 40 here. So of course this, because this is a linear scale, so this is the first block which is somewhere out here, it's a 6. So even if it doesn't look very straight line, as you might have guessed by now that my drawing isn't very good, so this is basically going to be the constant block. What about this block? You see this has a break frequency or a corner frequency at 0.2. So 0.2 would be somewhere around here, I reckon, almost close to halfway but not quite there. Yeah, so this is 2 times, so somewhere around here. Okay, maybe not here. Yeah, okay, so this is going to be like some constant line like this. Okay, so let us first turn our attention to just the magnitude plots, which we will see the phase plot later. So the next block we look at this is this blue one, which is just a first order 0. What is its break frequency or corner frequency? It's 0.2. So let us see where that 0.2 would be. So 0.2 would be somewhere there near about here, not exactly 0.2 on a linear scale, of course, yeah, but it would be somewhere over here, right? Okay, so now if that is what it is, then let us just mark this out here. So what does a typical block like this have? What does its Bode plot look like? We know that it looks something like this. Okay, so this is 0.2, it will probably come all the way until here, and then it will rise at 20 dBs per decade. So at 2 or thereabout, it will have 20 dB. At 20, which is somewhere here, it will attain this 40 dB, 40 dB value, right, because it is 20 dB per decade. So if I just join, this is going to give me a reasonably good approximation. Again, please excuse this drawing, it may not look like a straight line. Yeah, okay, that is somewhat better. Okay, so that is our blue block. What about the denominators, the integrator? Of course, we know that this is going to be a constant line at minus 20 dB per decade, which passes through the point 0 dB at 1. So immediately we draw this 0 dB line at 1. So the integrator line must pass through this, and it must descend at, so it is going to be 20 dBs at 0.1 here, and minus 20 dBs at 10 here. So now we have a reasonably good way of drawing the straight line. We have in fact 3 points, 2 points would have sufficed. So this is what the integrator line is going to look like. Let me try and draw it better if I can. Okay, so this is how the integrator's line is going to pass. Okay, the black one. Okay, what about this purple one? So this has got a break frequency at 10, which is a nice round figure. So it's got a break frequency at 10. So let me use a purple pen here. Again, it's going to pass through this 0 like this, all the way up to 10. Yeah, at 100, it's going to go 1 decade, 20 dBs below. So it's going to come somewhere here, and at 1000, it's going to go to 40. So I've got 3 points again, so I can draw a reasonably good straight line, I hope. Yeah, so that's the purple block. What about the green block? This has got at 50. So 50 would be closer to 100 than 10, because again, remember, this is a log scale, right? So we'll have 50 somewhere over here. So this is the other block. What color have I used, I wonder? Green. Okay, so let me use the green color here. So this is 50 somewhere over here. So let me draw the other block. So these are all overlapping, too many overlapping blocks now, right? Yeah, but that's what happens. So at over here it's 50. So near about 500 it will be minus 20 dBs, and near about 5000, which is probably somewhere here, it will be minus 40 dBs. Okay, so let me probably draw this 10,000 line or 10,000 here also. yeah. So this is the 10,000 point here, so this is 10,000, yeah. Okay, so now I can draw this passing through these 3 points, so they more or less look parallel. I probably give myself less credit as an artist, but it's pretty shoddy still nonetheless. So now we have done all of these individual plots. The idea is that we should be able to add them up together, right. So how are we going to do that? First, focus on what's happening at very low frequencies. You see, at very low frequencies, all these blocks, that is this blue, this purple and this green, they are all contributing 0 dB. What are the only two contributing factors at low frequency? This is a very important observation, and we shall see that this will actually help us in evaluating these so called error constants. Remember those error constants we had seen earlier, yeah, that Kv and that Kp and that Ka that we had seen earlier. It turns out that we can actually evaluate those error constants by looking at this magnitude plot of the Bode plot, right. This magnitude function, how it behaves, yeah, and particularly at low frequencies how it behaves. By looking at certain particular points, yeah, certain specific points, we can actually determine numerically what the value of this Kv, Ka or Kp as applicable to the system are actually. So it needs a bit of careful thought, but before that let me just try and at least sketch this one correctly. So you see, at low frequencies it is only this red fellow which is basically this constant block and the integrator that have some non-zero values, right. All the other first order factors, even if there were a second order factor, you know that the second order also has a low frequency asymptote of 0 dB, right. So these first order and second order factors having real or complex conjugate poles, yeah, and zeros, they would all contribute 0 dB as you go for very low frequency asymptotes. The only contributing factors would be the constant block and integrator and or differentiator, if there were any. In this case there are no differentiators, there is only one integrator, it is a type 1 system. So what do we do then? What we do is we simply raise this integrator. So let me use some other color, maybe I should use a probably a brownish color or something, or maybe use this color. Okay. So what are we saying? We are essentially saying that at low frequencies, until the first corner or break frequency is encountered, yeah, it's only up until this point. So up until this point, the only two factors which contribute something non-zero to this Bode plot are this red line corresponding to the constant factor and this black line corresponding to the integrator. But what is the sum of a constant line and a line with a constant slope? It's just that constant slope line raised by a constant bias, right. So therefore let me draw that. Let me just raise this by 6 dB, because we know that this is 6 dB, no? We saw that log 2 is 0.3, 20 log 2 is 6 dB, right. So let me just raise this by 6 dB and draw it until this point. Okay, again this doesn't look like much of a straight line, excuse me for that, yeah. So let me use the color that I had chosen, yeah. So then up until this point it's just the integrator line raised by 6 dBs. But what happens at this point? You see, at this point the integrator still keeps falling, but now this line, this blue line which corresponds to this 0 here, it starts rising, right. So therefore they nullify each other, yeah. So they will keep nullifying each other, yeah, until we encounter some other blocks. Okay, so how long will this continue? You might wonder, right. So yeah, so this then nullifies. What I am essentially saying is that there is a constant bias line which of course contributes nothing new, it just contributes that 6 dB throughout, yeah, it is just going to raise the whole plot. What about this integrator? The integrator keeps decreasing, but the magnitude by which the integrator decreases from this point onwards, that is from point 2 onwards, is exactly the same magnitude. So you see, at any point here the magnitude contributed by this blue line is exactly what is being taken away by this black line, yeah, from its value here, because they are both rising and falling at the same slope. So you take a point that is delta distance away from point 2, yeah, the amount by which the integrator would have reduced by now, the black line's magnitude would have reduced by then, is the exact same magnitude by which this blue line's magnitude would have increased by then. So they nullify each other. So therefore this value would be held at a constant from beyond this point. How long? Till you encounter the next break frequency, which is, if I draw carefully here on this line, somewhere here, which is my next break frequency 10. Yeah, remember when we were drawing this was the next break frequency 10, is it not? So at 10 I encountered this purple line. What does this purple line do? This purple line now, you see, begins to descend at 20 dB per decade, right? So this then, from this constant line that I was following, which was the cumulative plot, yeah, which was the cumulative plot of this entire system, this j omega, yeah, now it's being taken away, something is being taken away. So it's going to fall at minus 20 dB per decade until it encounters this green corner frequency here. From this green corner frequency, what happens? It takes away even more. So it starts descending. So this was minus 20 dB per decade. This was minus 20 dB per decade due to the integrator, right? And from here on, you see, it starts reducing even further at a steeper slope, right? So let me see if that slope probably doesn't look steeper. So let me make it steeper. So it starts reducing even further, yeah. So this then, from this break frequency onwards, now it gets to minus 40 dB per decade, and eventually you see it will descend at a slope that is equal to, it's again a no-brainer, it's going to be 20 times n minus m dB per decade, yeah. So n is the number of poles, m is the number of zeros, so it's n minus m is then the relative degree, yeah. So eventually the line will encounter no further, this plot will encounter no further corner frequency, so it will keep descending at the same rate of 20 times n minus m dB per decade here. Here n minus m is 2, there are 3 poles and 2 zeros, right. So therefore you will see that eventually it will descend at 40 dB per decade. Yeah, maybe I should put a minus sign here, because obviously n means a pole, so pole is greater, so a pole will have minus 20 dB per decade, yeah. So that's exactly the rate of fall. So that's why in control theory we often say that all control systems are of low pass in nature. What it essentially means is, so yeah, so that's another term you might encounter, low pass, yeah. So these will only begin to make sense once you understand Bode plot. You see there are more number of poles than zeros in a typical control system, right. So n is greater than m. So eventually beyond a certain frequency, after all the poles and zeros are to the left of that frequency, you will see that this Bode plot, this Bode magnitude plot, descends at a slope of minus 20 times the relative degree dB per decade, yeah. So eventually it cuts off, it attenuates frequencies beyond that point. So eventually you will see that this Bode plot of this control system, for a system that is actually strictly proper in fact, yeah. So a control system is generally strictly proper, as we've discussed so often in this course, right. So for such a control system you will see that it will always have a low pass characteristics, in the sense that it will try to amplify lower frequencies and it will always attenuate frequencies beyond a certain cutoff point, yeah, at higher frequencies. So that's why we say that control systems are generally low pass in nature. So that's some sort of a folklore that you might have encountered, but now you also see in the light of this Bode plot why that kind of folklore makes sense, yeah. It's not just old wives' tales, right. Okay, so now we are not yet done, because we still have to sort of figure out what this phase plot looks like, right. And here I put it to you that I am going to use this shortcut technique, yeah. So the shortcut technique, by that I mean, like, I am not going to take this break frequency, go 1 decade below and 1 decade above and try and join it with a sloping line. What I am instead going to do is, I am going to sort of make this approximation. I don't care about the discontinuity is what I'm saying. So I have a break frequency, I'll draw the high frequency asymptote all the way up until the break frequency, I'll draw the low frequency asymptote also all the way up until here, and let this be here, because at the end of the day I am going to approximate it somehow like this. Yeah, so if I am going to do that, how does it matter whether I am going 1 decade up and joining this line, or I am going half a decade up and half a decade down and joining by this line? Yeah, because this will, for a second order underdamped system, this will in general depend on this zeta, and for overdamped systems, or for first order factors, anyway I am going to do an approximation like this, no. So I am going to just ensure that in the corner, in the break frequency, at that value it takes 45 degrees, and how I am going to join the rest of it is completely up to my approximation skills. So yeah, I just want to draw as quickly as possible this Bode plot, and then gauge what the qualitative Bode plot looks like. If I am very particular about the exact numerical values at several points, I better use MATLAB or something like that. No, there is a command in MATLAB like Bode. Yeah, it is a command in MATLAB. So you can better use that then if you want very high accuracy. But if you just want a quick sketch, I am not going to take this trouble. So already in the phase plot I am going to use that. So what about the phase of this fellow, this red fellow here? Yeah, it is going to be a 0 slope. So the red fellow is going to contribute only a 0 throughout, no difference, right? What about the contribution of the blue fellow? The blue fellow, it turns out, will also have 0 all the way. The low frequency asymptote for the blue fellow will be all the way up 0 until here. So let me make this 90 degrees here and make this minus 90 degrees here. So the blue fellow, it turns out, will have a high frequency asymptote. Sorry, let me use the blue pen here. So the blue fellow will have a high frequency asymptote like this. So already I have drawn the phase plot for 2 different blocks. I am going to just add them, as we have seen that phase of the product of complex numbers is basically the sum of the individual phases. What about the integrator fellow? This is going to have a constant phase of minus 90 degrees. So let me draw a black line for the integrator, which is minus 90 degrees. Okay. What about the purple and the green fellow? The purple fellow will start to have a high frequency asymptote from 10 onwards. So let me use the purple fellow here. It's going to have from 10 onwards, so 10 is some point here. So the purple fellow is going to follow this line until 10, and then at 10 it's going to have this constant line. And what about the green fellow? The green fellow goes all the way up to 50. So the green fellow goes all the way up to maybe a point such as this, and from this point onwards it starts following the high frequency. So that is very simple now, right? These are just additions of constant lines here. Yeah, let me not just bother with those slopes and all those additions. Yeah, it makes matters complicated. I am, after all, interested in being able to draw this up quickly. Okay. So up until the first time I encountered this change due to the blue line, what is my value? See, at low frequencies, so let me use that again, that same color which I used for the overall Bode plot. So this color is basically the G omega Bode plot, okay, the magnitude. So this is the color I used for 20 log G omega, right? Now here also let me use this for the phase. Yeah, so let me use this color for phase. So you see, until this point, the overall sum is 0 minus 90 degrees. That minus 90 degrees, again the same thing here. You see, at low frequency, whether it is the magnitude plot or it is the phase plot, it is only those factors, the integrators and differentiators or the constant terms, that will contribute to this Bode plot. Whether it is the magnitude or the phase, does not matter. Yeah, all the other terms will contribute zeros at very low frequencies. Yeah, I could have gone even lower, no. This is, I have started with 0.01, I could have gone to 0.001, 0.0001, so on and so forth. So what is this telling me? It is telling me that at very low frequencies, it is just the sum of this minus 90 degrees, because it is a type 1 system. If it was type 2, it would be minus 180 degrees. Yeah, so it is a type 1, it is minus 90 degrees, and the constant term is contributing 0. So the low frequencies, they start at this minus 90, but then here at this point there is an addition of plus 90 degrees. Yeah. So this then goes like this until I encounter the purple line. Yeah, so I encountered the purple line here. What does the purple line do? Yeah, okay, I think I've made a mistake. Yeah, I have made a mistake. So purple and the green lines are going to contribute minus 90 degrees, right, at the break frequency. I've mistakenly drawn them above. Okay, so the purple and so the blue line is what contributes a positive 90 degrees. Yeah, sorry about that. The purple line actually contributes minus 90 degrees, right. So the purple line starts contributing minus 90 degree from 10 onwards. Yeah, minus 90 degree from 10 onwards, and so does the green line contribute another minus 90 degree from this point onwards, which is 50 onwards. Yeah, right. Okay, so now let me draw that, go back to the original sketch. That was a bad mistake I made, sorry about that. So we have this at low frequencies we have minus 90 degrees. From the first break frequency onwards at point 2 we have 0 degrees all the way up until 10. At 10 what happens now? Now you see again this purple line brings it back to terra firma. So this is going to be the purple line's contribution, it is going to pull it back again. So at this point what is the contribution? The purple line is contributing minus 90, the integrator is contributing minus 90, which is minus 180, the constant line, the constant factor is contributing just 0. Yeah, so no new contribution for the constant line, so it's 0. The blue line is contributing a plus 90 degrees, right. So there's minus 90, plus 90, so it's overall minus 90, right. But now at this point onwards, which is from 50 onwards, you see the green line also starts pulling its weight in, which is another minus 90 degrees. So let me just label that as minus 180 degrees here. So now you have a further addition of a negative 90 degrees, which is going to pull it back from here. So at least my asymptotes are clear. So now I know that the discontinuous, albeit, but this is what the plot is going to look like. So if I want a better sketch, I might make some approximation and maybe use some other color. What color should I use? Okay, let me use this slightly darker color here, a brownish one. So maybe I am going to just approximate this, yeah, approximate this and then this. I don't know, maybe some, if I want a more, as I said, if I want a more accurate sketch, I better draw this on MATLAB, yeah. So this is going to be my phase plot, yeah. Now having done all of these calculations and all of this effort, you might be a little bogged down at this point, yeah. I mean too many drawings and drawing these asymptotes, adding them. I mean we started under the premise that yeah, addition of functions, after all how difficult can it be. But at this point you might feel a little tired if you've been at least doing it the way I have been doing. You might feel a little tired, oh we have to keep tab of so many things. Isn't there an easier way to do this? It turns out there is. So now that we have gone about it in the long winded fashion, let me just try and do the same thing more quickly. And this is exactly the technique that experienced people would use, yeah. Now that we have convinced ourselves about the correctness of this plot, what we will do is, when encountered with a transfer function like this, we will not bother with all those nitty-gritties. So what we do is this, quickly we will draw this up. So we will see that we will account for this constant factor last. First we will just factor in for all of these. So what are my, again let me start here from 0.01, 0.1, 1.0, 10.0, 100, 1000 and 10,000, yeah. So let us just just consider the same thing as before, only difference is now we are going to consider this shortcut technique. Hopefully you will not feel as bogged down by this method as the earlier method might have suggested to you. So let us just mark out, first thing we do is we mark out the corner frequencies, the break frequencies. So here's 0.2, yeah, here's 10, yeah, 0.2 is somewhere here, 10 is somewhere here, 50 would be somewhere here. Of course, the integrator does not have any break frequency of its own. So we will account for these factors which contribute to the low frequency asymptotes last. So we will account for the integrator, yeah, or integrators in case this were a type 2 system, yeah, or zeros at the origin. Those factors we would account for last. First we will consider only factors like these, or if second order factors are present, we will only consider them. How do we go about this? So let us say this is my 0 dB line, yeah. So if this is my 0 dB line, how do I go about sketching this? This is 0.2, this is 10, this is 50. So what I will do is I will just go about starting from 0 dB till I encounter the first break frequency, and I ask myself, what is this break frequency? Is it corresponding to a pole or a 0? I see that it is corresponding to a 0, yeah. So I start raising this at 20 dB per decade. I start going about it like this, I raise it at 20 dB per decade until I encounter the next break frequency, and I ask myself whether it is a pole or a 0, yeah. So if it is a pole, then my slope will decrease by 20 dB per decade. If it is a 0, I mean a simple pole, that is not the complex conjugate, yeah. If it is a 0, it will again increase by 20 dB per decade. So this is 20 dB per decade, this is 20 dB per decade, now this is plus 20 dB per decade from here. But here I encountered a pole, so then I better draw it like this, because now it is going to be a flat line until I encounter the next break frequency, which again happens to correspond to a pole, right. So then I again start dropping at, okay, this does not look like 20, let me just add this. So this is 20 dB per decade again, but this is minus 20 dB per decade. All that is fine, but we are yet to account for this constant factor and the integrator. So what do we do? How do we account for this constant factor? Well, the constant factor is just going to raise this plot. So one way is, you can just lift this entire plot. So you can use a green line and lift this entire plot every point by 6 dB. So you can just say, now I am going to just retrace the same plot, sorry, this does not look good. So let us retrace the same plot here, just a parallel line at every segment you draw a line parallel like this and raise this here and the same plot, okay. Or I could have been lazy and I could have said I just relabel this 0 dB as 6 dB, yeah, I can just shift it. It is either way, you either bring the axis down or you lift the plot. It's really not any difference, it's just relative, right. Okay, so let me draw that a little better, yeah, okay, that's good, yeah, okay. But now we are yet to account for this integrator. How do we account for this integrator? Now you know that one thing is for sure, that at omega is equal to 1, this integrator must pass through the 0 dB line, yeah. So what do? The only thing that we have to now notice, the only thing we have to now add is the integrator. The other part of the sketch became very simple, right. Earlier, compared with this, we drew all those constituent blocks and then we kept drawing it very carefully like this, right. But here what we are saying is we do not need to do all of that, we just drawing these break frequencies or corner frequencies and just a bit of shifting. If you do not have an integrator, then you are done, this is it, your Bode plot is done, over. But because we have an integrator here, now we have to also be a little cautious about how to add this integrator. So the only thing that we have to know is, or be mindful of, is to add this integrator at every point. So we know this integrator is something that passes through this and has a slope of 20 dB per decade. Has a slope of 20 dB per decade and passes through this. So what does this integrator do? Yeah. Let's see, this is, yeah. So what does this integrator do? Right? It will not raise the plot by a constant factor, of course. Instead, it will make some more drastic changes to this plot. Yeah. So then you see it's not that difficult. You see what happens basically is, yeah, right here. So if I extend this y axis like this, where will this integrator indeed add up? So at this frequency of 0.01, wherever it is you are starting this, yeah, you see what is the net contribution before the addition of the integrator? It was starting from here, this green line. But now you have to add this integrator up. So what is the contribution of this integrator? The contribution of this integrator is this much. So now you add that much to your existing plot, and this is where now your plot will start from. Simple, that's it. That's just it. So once you have figured out this point, whatever was the length of this, where the integrator was cutting this at whatever frequency you started sketching, you cannot go all the way down to 0, remember, because it is a log scale, right. So you are starting at some non-zero frequency here. At that non-zero frequency, you see where this line with a slope of minus 20 dB per decade and passing through 1, 0 cuts this your y axis. Yeah, this y axis may vary from person to person. Yeah, I might have gone, as I said, all the way down to 0.001, but wherever it is, at some point we have the y axis drawn. So wherever you are drawing this y axis, think of its intercept, the y intercept at this y, wherever you have drawn the y axis, and from the now wherever you have this low frequency asymptote, raise the level by that. So if this is equal to, let us say, L, then this is now equal to L plus, what is this, 6 dB. So this is L plus 6 dB, that is the point here. Yeah, if this length of this intercept is L, then this is now L plus 6 dB. Why 6 dB? Because I know that 20 log 2 is 6. So whatever was the constant value, you pass it through 20 log, 20 times log of that, yeah, and add that to L. That is it. What do you have to do next? What you have to now do is, let me draw the final plot in red. So what you now have to do is, you see here the Bode plot has a slope of 0, but this integrator contributes a slope of minus 20 dB. So you just have to be mindful of that. Wherever you had whatever slope, now you add a slope of minus 20 dB per decade to that existing slope. That is it. That is exactly it. So, and you are done. So now what you do is you draw this Bode plot, sorry, again not a good enough straight line. So now you draw this Bode plot all the way down till here. Yeah, and at this break frequency, you see the green line had a slope of plus 20 dB per decade. So you will have a slope of 0, and you go on like this until at this point you see the green line had a slope of 0 dB per decade. So you will again have a slope of minus 20 dB per decade, and again at 50 you see up from 50 onwards this has a slope of minus 20 dB per decade. So you must have a slope of minus 40 dB per decade, and that is it. So this is my 20 log Gj omega, just like that. Yeah. What did I do to summarize the steps? Draw up the corner frequencies, yeah, draw a flat line up until the first corner frequency, then ask what the corner frequency corresponds to. If it is a pole, then you take a slope of minus 20 dB per decade from thereafter. If it is a 0, you take a slope of plus 20 dB per decade thereafter. Go on till the next break frequency you encounter. At each break frequency you encounter, ask the question as to whether it is a pole or a 0. If it is a pole, you will add to the existing slope prior to that, whatever was the existing slope, you add to that minus 20 dB per decade. If it is a 0, then you add to it plus 20 dB per decade, and you are done. Then you lift this entire plot by 20 log of k, where k in this case is 2. 20 log of k, lift it. And now if you do not have any integrators, you are done. If you have any integrator, then you have to now add this integrator. So in summary, if you want to now encapsulate all of this, if you have an integrator, if you want to start and do not want to add this integrator as an intermediate step like here, here also you might feel a little bogged down after all, right, because it does not seem very obvious. So if you have an integrator, or rather R integrators, then initially your slope will be minus 20 R dB per decade. Yeah, R could be 1, R could be 2 depending on the type of the system, R is the type of the system. So you start with that at very low frequencies, you start with a slope like that, yeah, but where will this intercept be, that is still a crucial point, right, that is something that is not very obvious, yeah. So for that you really need to find out what this k is. So what I am saying is, in other words, you can try merging these two together, the constant term with the integrator together. So instead of thinking of 1 by j omega, you think of 2 by j omega, yeah, and you see what happens to this at omega is equal to 1. So you see the magnitude of this is going to be 2 by omega, right. So then you see at omega is equal to 1, instead of the original integrator which had a value of 0 dB, this will now have a value of 6 dB, yeah. So therefore, if you really want a quick shortcut, now let me give you a really quick shortcut. So this is going to be not the phase plot, let me redraw the same thing again. So here is the trick that we have now learned. So you merge the constant term with the integrator together, right, and then you look up what this is, right. So you take the 20 log of this, that is equal to the 20 log of 2 upon omega. So this obviously at omega is equal to 1, this is 20 log of 2, which is 6 dB, right. So omega is equal to 1 is always going to be an important point for you if you have an integrator in a system. So now let us see, this is 0.2, this is 1, this is 10, this is 50, and that is all that you care about. So then you know that at 1, yeah, you take this 20 log of 2, that is it, yeah, and you extend this line to the left with a slope of minus 20 dB per decade, yeah, and that is it. Now it is very simple, once you have accounted for this factor, now it is very simple. How? Start with this plot here, start with this plot here. The first time you encounter a corner frequency or a break frequency, ask yourself if it is a pole or a 0. Since here it is 0, your slope would increase by 20 dB per decade. So earlier it was minus 20, now it will become 0, right up till here. Then you encounter the next break frequency, I think at 10 here, which happens to be a pole. So here your slope will diminish by 20. So from 0 it will go to minus 20 dB per decade, and so it will continue until the next break frequency. Here this also happens to be a pole, so it will decrease by another further 20 dB per decade. So it will come down even more like this. So this is minus 40 dB per decade, this is minus 20 dB per decade. So in summary, what we have shown you is that given any transfer function like this, you will quickly be able to sketch the asymptotic Bode plot. Of course, this is only the magnitude part. So to complete the picture, I should also give you a quick way of drawing the phase plot. So let us say this is omega and this is phi of omega. So let us say you have 180 degrees, 90 degrees, 0 degrees, minus 90 degrees and minus 180 degrees, okay. So here also you see this 2 will no longer be of any consequence, the only thing we are concerned with is how many integrators are there. So we ask ourselves how many integrators are there, there is only one integrator. So if there are R integrators, we start at a value of minus 90 times R. So here it is, this R is 1, yeah, and okay, the first thing again as usual we do is draw out the break frequency, it is 0.02, 10 and 50. So let me just quickly draw that out here, it is 0.01, then it's 0.1, then it's 1.0, then it's 10.0, then it's 100, and then it's 1000, right. Now, we know that because of this phase function, right, there is only one integrator, so we start with as many integrators, so we start with minus 90 times r, if r is the number of integrators. So we start at minus 90. What are our break frequencies? Let me mark that out first. So everything, the entire Bode plot hinges on locating these break frequencies. They are 0.2, 10 and 50. So let me mark that out again. So this is 0.2, this is 10, and this is, let us say, 50 over here. So what I am going to do is now quickly I start with what is my low frequency asymptote determined by the number of integrators, otherwise it would have been 0 if there were no integrators. So I start at this, I start like this. First break frequency I encounter, I ask myself, is it a pole or a 0? If it's a 0, then I raise the asymptote by 90 degrees. If it's a pole, I would have gone down by 90 degrees. So I continue with this asymptote until I encounter the next break frequency. At the next break frequency, I ask myself if it's a pole or a 0. The answer is it's a pole. So I go down by 90 degrees. Then again at the next break frequency, I ask myself, is it a pole or a 0? And it happens to be a pole, right. So again at minus 180 degrees, I settle down for. So now I have this, albeit a very discontinuous and bad looking, you might say, phase plot, but I at least have a rough idea. And once I have this, it's a very good place to at least get started with. I can now start approximating this. Maybe I should use the green color. So I can start approximating this like this. Yeah, maybe I don't know how it will exactly look. It will probably not go all the way up, this green fellow. So it's probably going to go like this and something like this. Yeah. So you see, this phase plot and this magnitude plot, the idea of this alternate discussion was, or this extended discussion was, to convince you that this initial plot, even though after all it is just a sum of few constituent blocks, it might seem like very congested and messy, but at the end the observations that helped us piece this together told us that all that you need to bother with are just drop the break frequencies. Yeah. Once you have drawn up the break frequencies, the next question is how many integrators are there. For the magnitude plot also, that factor k plays a role. So instead of taking the integrator alone, let the integrator be combined with this constant factor. Yeah. And once you merge it together, you should be now able to sort of sketch the magnitude plot, at least the asymptotic version of it, fairly easily. That is going to be a pretty easy job. So the important thing to note from here is, the important observation is that, see, if you have a type 0 system, there is no integrator, you will see that the low frequency asymptote of the magnitude plot 20 log m omega would be some constant line like this. Yeah, this is the low frequency asymptote. If you have a type 1, yeah, then you will see that the low frequency asymptote, the same low frequency asymptote of the magnitude function, it goes down with a slope of minus 20 dB per decade. So that is going to be a low frequency asymptote. If you have a type 2, and you can similarly keep increasing the type, yeah, it's really not going to make much of a difference. But since we have discussed type 0, type 1 and type 2 vis-a-vis the position error constant, the velocity error constant and the acceleration error constant, which is now what we are going to try and figure out from these Bode plots. So you see here you will have similar nature as type 1, except for the fact that now it is going to descend at minus 40 dB per decade. Yeah. Now the point I am making here is that, you know, based on these Bode plots, suppose here this was the direct question. Someone's given you the transfer function already. So if someone's given you the transfer function, then all that you need to do is you need to evaluate, in this case you need to evaluate g of 0 In this case we have limit s tending to 0 s times g of s, and in this case our variable of interest is limit s tending to 0 s squared gs, and we know that these have been given the name of kp, kv, the velocity error constant, and of course ka. So now the question is, given that we do not know the closed form expression for the transfer function, and someone has just given us the sketch of the magnitude plot of the Bode plot, and we are asked to determine what these position constant, velocity constant, or the acceleration constant are depending on the system. So if it is a type 0 system, then what is the position constant? If it is a type 1 system, what is the velocity constant? If it is a type 2 system, what is the acceleration constant, is the question before us. So how do we go about this? You see, the hint is there in this earlier construction, and it is for this specific reason that I focused on this particular method of drawing it up. Yeah, I could have just shown you this method, shortcut, right, immediately, and you could have just started sketching, but I wanted to show you how this came about, in the sense that how we merged this constant term together with the integrator and then drew the overall plot. Okay. So you see here, now if you think about it a bit, what is this s times gs? Yeah, if you know the Bode plot of g j omega, the Bode plot of s times gs, that is j omega times g of j omega, is nothing but a differentiator that is added to this existing Bode plot. Yeah. Similarly, if you have this type 2 plant and you have been given the Bode plot, all that you need to get this s squared gs, so that this limit exists, yeah, is to multiply this by a double differentiator, that is a line with a slope of 40 dB per decade, which passes through omega is equal to 1. That is the crucial bit of information. It passes through omega is equal to 1 with a value of 0 dB, right. That is the most important observation. Why am I saying that is the most important observation? Again, cast your attention back here, right. Now suppose I were to add, so this is a typical type 1 system. Suppose I were to add, let me draw with a dotted blue line, a differentiator to this, right, like this, and then try and find the equivalent of this, yeah, the resultant of this. What would that resultant be? Yeah, you see, at omega is equal to 1, this differentiator contributes only 0 dB, that is nothing, right. So it contributes nothing at this particular value, okay. But if you notice now a bit carefully, this and this integrator and the differentiator have the same slope, yeah. So they end up nullifying each other in the sense that the sum of these two is a particular constant, and what is that constant? That constant is nothing but this additional factor, because at this omega is equal to 1, the differentiator contributes 0, whatever contribution is there is due to the integrator, right. In other words, what I am saying is, if, let me take a new slide to make it clearer, as I had drawn earlier, this, okay. Suppose this is our magnitude plot that has been given to us, okay. Now with this magnitude plot, someone tells us, hey, I want you to find out the kV, because this I know is minus 20 dB per decade, and therefore this is a type 1 system. So someone asks us, what is the kV value? What are we going to do in that case? So what we are going to do in that case is, we are going to extend this, we are going to extend this plot. So suppose somewhere here is omega is equal to 1. So we are going to extend this plot like this, yeah, and the claim is that wherever this gives me this value, yeah, this is going to be my, so let me just focus my attention back here, yeah. So if I had extended this original plot here, yeah, this integrator starting from here and all the way down till here, you see it would exactly intercept at 6 dB. Why? The reason is pretty obvious. You see, you originally had this 0 dB line here, then because of the factor of 2, you raised it by 6 dBs here, and then this integrator also got raised by 6 dB. So originally this integrator without this 2 would have passed through this point frequency of 1 and 0 dB. So it would have intersected with the 0 dB line at a frequency of 1, yeah. But now at the same frequency of 1, instead of intersecting with the 0 dB line, yeah, it intersects some other point, yeah. So if it's raised, if k is greater than 1 for instance, yeah, so then, yeah, let me draw this carefully here. So then you read off this marker, yeah. So what is this reading? Let us say this is k, this is exactly what your 20 log kV is, that is the claim. So let me explain that a little clearer, maybe this figure is a bit too cluttered, but still I will make use of this figure because this is a good example, yeah. You see originally you had this 0 dB line, then because of this factor of 2 it got raised by this, and then we saw that the integrator also got raised by the same factor, and the eventual net resultant Bode plot was this red line, yeah. So this red line, yeah, if you extended this initial, the low frequency asymptote which was due to the integrator, yeah, but now it is not just the pure integrator, it is this integrator containing the gain incorporated within, and this gain is after all what we are trying to figure out, right. Of course in this case we know what it is, but in this case we do not have the luxury of knowing what that gain is, but eventually we are sure that this initial minus 20 dB per decade line starts in such a way that at omega is equal to 1, if I read this off, if it is exactly 0 dB, then of course the gain is unity, because it is a pure integrator with a unit gain. But if it has some non-unity gain, then that non-unity gain is nothing but kV, yeah, as I have seen here. So I know that this is going to be my kV, I know that S GS limit S tending to 0 is my kV, right. So because of that knowledge that I have, this is nothing but 20 log kV, yeah. So the trick is that if you are given a type 1 system like this, what you do is you take this initial low frequency asymptote due to the integrator, keep extending it and see what value it takes in decibels at omega is equal to 1, yeah. So that value divided by 20 and then 10 to the power of that, right, that is going to be your kV, okay, simple. The same trick you can do for, not the trick rather, but the same thing you can apply. So you can take this as an exercise, that the same principle you can apply to a type 2 system as well, only thing that this will now be minus 40 dB per decade, yeah, but the principle is still the same. I might have had 2 integrators here and the plot would have then been minus 40 dB per decade, the rest of it would have been still the same, right. So there is no difference here. So the point is that if you want to now evaluate Ka, then what you do is, let us say you have this omega is equal to 1 here, so you extend this line all the way down to here, yeah, and whatever is your reading here, this is going to be your 20 log of Ka, alright, that is it, that is just it, right. So all that you need to do is, given a higher type system, not a type 0 system, yeah, you just read off this. Of course now you might ask, what about a type 0 system? That is pretty obvious, you know, you look at this typical type 0 system, its low frequency asymptote would be a flat line like this. Why? Because there is no integrator or differentiator, right. So you just read off this intercept and this is going to be a 20 log Kp, straightforward. This is the simplest case of all. So this is for type 0, you read the position error constant, for type 1 you read the velocity error constant, and for type 2 you read the acceleration error constant. It is the same thing, yeah. So you take this as an exercise to verify or convince yourself that this works for a type 2 and therefore by extension for a higher type system. Now before we conclude this particular segment of the lecture, let me just explain another point a little more carefully, which I might have glossed over a bit earlier. So you might be wondering about this 3D plot, in case you are thinking what is this 3D, I mean why is he saying that it is a distance from this pole to this thing, to this point, right. See, after all, what are these factors? If you take a first order factor, it is basically this j omega tau plus 1. So what is this? If you just take this tau out, it is nothing but j omega plus 1 by tau, and by now we are very familiar with this. This is nothing but j omega minus 1 by tau, yeah. So that is basically like saying that this is the point j omega, yeah, and you are finding out the distance of the point minus 1 by tau from here. So, minus 1 by tau is probably somewhere over here. By the same token, if you now have a second order factor, if you allow for complex factorizations, it is going to be nothing but j omega by z1 plus 1 times j omega by z2 plus z1 conjugate rather, z1 conjugate plus 1, but z1 is a complex number. So, by the same token, now you can call this z1 conjugate and you can call this z1, right. So, if at a particular frequency you are evaluating this second order factor, all that you are doing is basically measuring off the distance of the point j omega, which is this, from minus z1 and from minus z1 conjugate. So, as I explained earlier, as you increase the damping, this rotates further and comes closer to this real axis, and therefore its distance from, of course, under the assumption that this length of the segment does not decrease, that is omega n remains fixed. So, then it only rotates and comes further and further from the imaginary axis, and therefore the distance increases. So, if it is a pole, right, if it is a pole, then its distance increases, means the distance is sitting in the denominator of the transfer function, therefore the effect decreases, therefore the magnitude function decreases. So, the further the pole is to the left, the lesser is the magnitude. In other words, the more the damping is, the lesser is the resonant peak. Yeah. So, this in general holds for all of these transfer functions. If you on the other hand have a 0, yeah, if on the other hand you have a 0, then the closer the 0 is, yeah, then you see that the distance from the 0 is small, yeah, and if the distance from the 0 is small, then what do we know? It is in the numerator, so the impact is smaller. On the other hand, if the 0 is very far, right, the 0 is very far, then the distance is longer, and therefore the numerator function increases in magnitude, right, yeah. So, that is essentially it, right. So, of course, in case of the 0, you have these undershoots, I should not call them undershoots, I mean you have these resonant peaks in the reverse direction, in the negative direction. So, that is one point I really thought I should explain a bit, yeah. So, hopefully you have enjoyed this lecture, and with that we come to the end of this. In the next lecture, we shall see a few more interesting features of this Bode plot, and we shall learn about a few more terminologies which we encounter pretty often, but now in the light of this Bode plot and our understanding thereof, things will be clearer.